In this final video, you are going to complete the design of the standalone PV system by simulating its performance. In particular, here you will learn about the control strategy that will be implemented to make the PV system operate at its optimum efficiency. Then we shall determine the performance of the PV system and finally carry out a design check to verify if the design meets the requirements. Let us first recap the concepts covered in the previous two videos. First, we derived the expressions to calculate some important electrical parameters of the PV system. Those are the current entering the charge controller, ICC, current leaving the charge controller and entering the inverter, IM, and the current and voltage of the battery bank, IBB, and the VBB. All this was followed by accurately sizing the different components of the PV system. In the next step, you are going to implement a control strategy mimicking the functions of the charge controller. The charge controller not only regulates the flow of current in the PV system, but also prevents the batteries from getting overcharged or over-discharged. The charge controller prevents overcharging of the battery bank by disconnecting them from the PV array. Similarly, they prevent over-discharging of the battery bank by disconnecting the loads from the battery bank after the batteries reach a certain level below the state of charge value. In the control strategy algorithm, a switching mechanism is set up to mimic such functions, typically operated by the charge controller itself. Further, the algorithm presented here is based on monitoring the state of charge, SOC, of the battery bank. Depending on the calculated state of charge, the switches are either open or closed. For example, during a PV generation, when the SOC of the battery bank reaches 100%, the PV side switch is opened and the generated energy is subsequently dumped. In the control strategy algorithm, this means that the parameter E dump is calculated. On the other hand, while feeding a load, when the battery bank SOC goes below a specified lower limit, the inverter side switch is opened. This means that the battery will fail to supply energy to the loads. In the control strategy algorithm, this means that the parameter E fail is calculated. The algorithm is overall implemented by looping it through a full year time period. Note that every loop corresponds to the time step that you choose during the beginning of your design. Now, let us look at the various steps followed by the algorithm. The first step is to set a starting state of charge value of the battery bank. Then, in the second step, begin the time loop and sense whether the switches are opened or closed. In the third step, calculate the battery bank current IBB for that instance in time. Follow the procedure discussed earlier to determine the battery bank current. In the fourth step, based on the IBB value, whether it is positive or negative, calculate the instantaneous state of charge of the battery bank. Then, from the new SOC, calculate E fail or E dump if applicable. Finally, in the last step, act on the charge controller switches based on the calculated new SOC and repeat the loop for the new time step. In summary, the steps 2 through 6 are looped throughout the entire year for every time step to determine the instantaneous values of the different parameters such as state of charge, battery bank current, etc. After we have simulated the control strategy by looping it through a full year, some performance parameters of the PV system are determined. The annual energy delivered by the PV system to the loads is determined first. It is calculated using the following expression. Unlike the grid-connected PV system, here the AC energy delivered by the PV system is calculated by subtracting the energy the system failed to deliver to the loads from the sum of total energy demand of the loads and delta EBB, where the parameter delta EBB denotes the difference in energy stored in the battery bank between the beginning and the end of the year. Also, from the above expression, we can see that due to the fact that E fail is a positive value, the AC energy delivered by the PV system is always lower than the total energy demanded by the loads. Thus, the loss of load probability for the PV system is calculated next. As you know, it is defined as the ratio between the energy that the PV system fails to deliver to the loads and the total energy requirement of the loads. By calculating the value of loss of load probability for the PV system, the level of autonomy achieved can be analyzed. Moreover, the PV system design can be evaluated before approval by looking at the calculated loss of load probability. If the loss of load probability is acceptable, and this depends on the application of your PV system, the calculated dumped energy by the PV system is assessed. If the E-dump value is low, the system is approved. If the E-dump is high, the PV array sizing is adjusted by downsizing it, and if the E-dump is 0, the number of chosen autonomous days can be reduced. In this case, it will potentially reduce the size of the battery bank and eventually bring down the costs involved. On the other hand, if the loss of load probability is not acceptable, either the PV or the battery bank size is adjusted by acting on their corresponding sizing factors. With this video, we come to the end of the detailed design of a standalone PV system. You studied the final steps needed to complete the design of a standalone PV system using the detailed design strategy. By implementing a control strategy, you were able to regulate the battery bank current and simulate the performance of the PV system. Finally, evaluating the loss of load probability, the PV system design can be approved when the calculated LLP value is within acceptable limits.